Hi, my name is Garcia, and today I'm going to be working on topic problem number 27 from page 829. The problem reads, in which solution will nitrous acid ionize less than it does in pure water? So before we start the exercise, I'd like to define the common ion effect. So the common ion effect says that in order to drive the reaction to the left, there must be a common ion between both compounds in the reactions. This means that the degree of dissociation of a weak electrolyte is lowered when there is a common ion. So that means that when there is a lower dissociation of the acid, there is a higher pH, meaning that it would be less acidic than it is in pure water. I like to separate these into the respective ions, so sodium chloride into sodium chlorine. Here there's no common ion with nitrous acid. If we do the same thing for potassium and nitrate, there's no common ion, and same goes for sodium and hydroxide. However, when we separate these two into its respective ions, we find that there is a common ion between nitrous acid and sodium nitrate. So, as I mentioned, when there's a common ion, that means that there's a higher pH rather than when it reacts with water. So the ideal way to solve this solution would be to create a rice table in pure water and then later using this compound. So we set up the reaction as if it were in pure water, assuming that there is 1 molar of reactant. So then there's 1 molar, and we set up the rice table as normally. So then we get Ka is equal to the concentration of the hydronium ion plus the concentration of the nitrite ion over the concentration of nitrous acid. So the Ka, as looked up on the chart of nitrous acid, is 4.0 times 10 to the minus 4. And then that we equal to x squared over 1.0 minus x. Unfortunately, because of the Ka, x is not small, so we have to cross multiply. So when we cross multiply, we get the expression x squared plus 4.0 times 10 to the minus 4 x minus 4.0 times 10 to the minus 4 is equal to 0. So then when you put that into the equation, you get negative 4.0 times 10 to the minus 4 plus minus the square root of 4.0 times 10 to the minus 4 squared minus 4ac over. So when we put that into the calculator, we get is 198. And we get 0.0202. So then since this is a negative value, then we can't use it. And then finally, to find the pH, we get minus log of the concentration of the hydronium ion, which would be 0.0198, And when we put that into the calculator, 1.7. So the pH of nitrous acid in pure water, of 1 molar nitrous acid in pure water, is 1.7. So that is very, very acidic. Once we do the rice table for the next reaction, so then we do nitrous acid aqueous plus water is in equilibrium with H3O plus NaNO2 aqueous. Now, we don't have to balance this reaction because sodium is a spectator ion. Now we do exactly the same thing, but instead of having 0 molar, we are going to have 0.0 molar. So then this is 0, and this is 1 molar. So then we do the same thing that we did in the previous equation, which would be concentration of the hydrogen ion plus the concentration of nitrite over the concentration of nitrous acid is equal to the Ka of nitrous acid, which is this value right here. And once you cross multiply, you would get the expression x squared plus 0.1004x minus times 10 to the minus 4. So you plug that into the equation. When we put this into the calculator to find x, so then this value of x is 0.00384, and then the other value of x would be negative 0.104. So again, since this is a negative value, we can't use it to determine the pH. So we would do negative log of 0.00384, that this is 2.42. So as you can see, the pH that we got using 10 molar of a common ion is a higher pH, therefore it is less acidic than the pH that we found in pure water. The correct answer is D.